I am just a 2D shape on your screen, but you are a three-dimensional object in space. Today we're exploring the marvelous geometry of 3D. We're starting off with the basics, which I'm sure most of you know. The volume of a cube with side length. The volume of a cube with side length at A is just A cubed. The surface area of a cube with side length A is 6A squared. And the length of a space diagonal in a cube, it's just A times root 3. And the reason this is true is because we can just apply Pythagorean theorem multiple times. So over here, Pythagorean theorem gives A root 2. And now you use Pythagorean theorem with this A here to get A root 3. So space diagonal is root 3 times the side length in a cube. Now let's just try a simple example just to review everything. What is the volume of a cube whose surface area is twice that of a cube with volume 1? So the cube with volume 1, let's say we have two cubes, right? Let's say the cube with volume 1 has side length A, so A cubed equals 1. And let's say the cube that we're trying to find the volume of let's say that cube has side length B. So we're asked to find B cubed. Now, what is this condition? The surface area, this new cube we're trying to find the volume of, has a surface area twice that of the cube with side length with volume 1. So I'm just going to write here, cube A, right? This is the cube with side length A, and the volume of a cube with side length B. Side B, side A, right? And we're given that the surface area of the cube with side length B is twice that of the cube with side length A. So what is the surface area of a cube with side length B? 6b squared, right? Each side of the cube face is b squared times 6 faces of the cube. For the cube with side length A, it's just 6a squared because each side is A. And we're given that the volume of, or the surface area is twice that of this cube. So the surface area of this cube with side length B, which we let it be, have a side length of B, is twice that of the cube with side length A. So we know that this is going to be 2 times bigger. Cool, so now we can cancel out 6 from both sides. We get B squared is 2A squared. Now we can take the square root of both sides. To get B is root 2A. And now we can plug it in over here. That means B cubed is root 2A cubed. And root 2 cubed is just root 2 squared times root 2, which is 2 times root 2. So 2 root 2 A cubed. Oh, aha! A cubed is 1. So this is just 2 root 2. And we have our answer. An easier way of looking about this is that if the surface area is twice that of if the cube which has a surface area that's doubled of the other cube, then its side length will just be square root of that. Because if you think about proportions, the cube with double the surface area has to have square root 2 the side length, so the area of each face is 2 times bigger. And then after that, we just see if the side length is square root 2 times bigger, the volume is root 2 cubed times bigger. So just 2 root 2. That's another way, little less formal way of doing it as well. Okay, now let's talk about prisms. The simplest prism is a rectangular prism. It's like this, as you can see. Like an elongated cube, I guess. So the volume is just length times base times height, of course, and the surface area is 2 times length times base, 2 times base times height, and plus 2 times length times height. So basically, there's 2 of each of these faces, right? We have like a face here. We have the same face on the opposite side. So to find the surface area, we just take 2 times every combination of the 3 dimensions. So length times base times height, length times height. And the space diagonal of a rectangular prism, again, we can just use Pythagorean theorem 2 times. To find this diagonal over here, it's square root of L squared plus B squared. To find this diagonal over here, it's this squared, it's the square root of this length squared plus this squared, right? This squared is L squared plus B squared. This squared is H squared. So the space diagonal squared is L squared plus B squared plus A squared. So it's equal to the square root of that. Just Pythagorean theorem applied 2 times. And the volume of a prism is just the base area times the height. The surface area of a prism is a cool way to do this. And this works for any prism I'm talking about, not just a rectangular one. Let's say we have some weird kind of funky prism like this. Doesn't matter, it could be anything. Or let's make it a little bit simpler so I don't have to draw a complicated diagram. Let's say we have a prism like this. As you can see, it's not rectangular because it works for any prism, not just a rectangular one. How do we find the surface area of a prism like this? And the key definition of a prism are the two bases are parallel. So the two bases of a prism are always parallel. So to find the surface area, we just find the base area, 2 times that, one for the top and one for the bottom. And then what we do is we multiply the height, which is constant throughout the whole prism, times the perimeter of the base. And that gives the lateral surface area. Okay, now let's try an example that is prisms. The figure below shows a polygon A, B, C, D, E, F, G, H, consisting of rectangles and right triangles. So this is a net, and a net is just basically, if I take apart some 3D object and open its faces, that will form a net. So you can fold it into the 3D object. When it cut out and folded along the dotted lines, the polygon forms a triangular prism. So a prism with triangle as its basis. Okay, suppose that AH is 8, EF is also 8, GH is 14. Where's GH? G is here, H is here. So this whole thing is 14. And we're asked to find the volume of the prism. So let's draw what this prism will look like. It's going to look something like, let's use a different pen. It's going to look something like this. Where we have, as you can see, we've got 2 triangular regions. And then we can imagine that over there as well. So this is what the prism will look like when it's folded. Why will it look like that? Because look, this is the base, right? So it's going to get folded here. And then this is the central part, which is this part over here is going to be the central part. And then this is the other base of the prism. And then this is the back part, so this part over here. And if you imagine it, it's folded on the dotted lines, which means this, if you can try and visualize in 3D, if we're going to fold along this dotted line over here, AB will go to BC. These two will join together. These two, let me mark them, will join together, and they'll join together to form this edge over here. Let me mark this. They'll form this edge when they combine together, right? Because as you can try and imagine, you fold along the dotted edge, they connect along over here. And similarly, if we fold along this edge, let's use red this time. Red. So this over here and this over here, they'll connect to form this edge here by the same logic. So this is like 3D visualization, which it's a good thing to try and improve for getting better at these 3D geo problems. But wait, so this is 8, and that means GF should also be equal to 8 because they meet together, and which means they must have equal length. So this is also going to be 8 as well. Okay, now GH is 14. So notice here that these triangles, they must be congruent because they're two bases, and prisms bases, they must be identical. So how do we use this condition that AH is 8? Well, this is a little bit more tricky to understand, but if you try and look at this diagram over here, hopefully it makes more sense. This triangle, of course, goes here, and then this thing over here, ABJH, this will be folded over and form this part of the prism. And notice how this edge will be the one that goes here. And it will touch CI. It will touch CI because CI is going to be folded up to form this edge. AB will be folded down on this edge. Or sorry, AH will be folded down and form this edge. And so will CI when it's folded as well. It will form this edge as well. So these two edges have to be equal. And because AH is 8, CI should also be equal to 8. So to find the volume of a prism, we essentially need to know the base area and the height, right? As you can see, GF over here is the height of the prism. GF is 8, so this part is also 8. So we've already found the height. Now we just need to find the base area, or maybe the dimensions of the base. These are both right angles, so that will probably be useful. So notice how CI is 8, right? So that means this is also 8 in the prism. Okay, so we found the height, and we found one of these dimensions of the base. And just to be clear here, this is the base of the prism. These are both the bases of the prism, and this is the height, right? A prism is kind of like a rotated prism, if you think about it. But the bases have to be the same on both sides. So it can't be something like this, because there's no other side on there. These are both bases of the prism. They have to be parallel. And as you can see, if you visualize it, it's parallel. Okay, so we have the height. We have one of the dimensions. We should try and find this over here. If we can find this length, we can find the base area and then multiply that by the height. But how do we find that length over there? Well, this length is also going to be equal to this length. So notice how this length, okay, let's mark it here. Make it a bit thinner, that's way too thick. Use a different color. So this over here corresponds to this over here when it's folded. And this over here corresponds to this over here. They're both equal, as you can see in the diagram, because the bases have to be parallel, so the bases are congruent. This part equals this part. So this whole thing is 14, right? We have to somehow try and use that fact. So when you're stuck in a geometry problem, a good strategy is to look for what you haven't used yet. We have not used this condition yet. So how should we use this condition? Well, we're trying to find this length over here, right? Because if we found the length of this, then we could easily find the base area, half base height. And then we would just multiply by height for volume. But we already discovered that this is the purple part over here. It's equal to this part over here. And we know this whole thing is 14. So if we can find, so we're thinking backwards here, as you can see, which is also a good problem solving strategy. If we can find the length of that region over there that I just marked, this one, then we could just do 14 minus that length to get the length of GJ over here. Or sorry, JG. Which is equal to this length, which is equal to this length, which is what we were trying to find. So how can we find the length of HJ? Notice how this over here is a rectangle, right? And the prism, as you can see, it's a rectangle over here. Even though it's a little tilted, that's because it's a 3D drawing, right? So this over here is a rectangle. It's this rectangle over here. So AB, as we already saw, will fold down to BC. So AB will fold down over here. We already discussed that. Oh, but this is going to have the same length as 8 because of these lengths are going to be equal. They have to be equal, after all, because this is a rectangle. And if it's a rectangle, this must be equal to this. And it has to be a rectangle because a prism definition is that the height is going to be consistent throughout. So this has to be a rectangle, and the height of a prism must be consistent throughout the whole prism. So if this is 8, this also must be 8 because the height is consistent throughout. And we've already discovered that this is just BC and AB both folded down. So both of these will have length 8 because we cannot fold something if AB is, let's say, tiny like this big. We can't fold it down and have it meet C. These two have to have the same length if we fold them together. And this length is 8, so AB must be 8. But then this is another rectangle. So that means that this must be 8 as well. This over here, again, just to remind you, it corresponds to this thing over here, which may not look like a rectangle, but is one because it's 3D. It's a 3D drawing. So this is a rectangle as well. It has to be by prism properties. This is 8. This is 8. Oh, but the whole thing is 14. So this extra part must be 6. And that extra part, as we already discussed, corresponds to this length over here, or this length over here as well, since these two lengths have to be equal since the bases are congruent. So the volume of this prism is just going to be equal to the base area times the height. The base area is just the area of this triangle, which is 6 times 8 divided by 2, right? Half base times height. And the height is just, well, 8. So the volume over here, 8, 2 cancels to form 4, is just 48 times 4, which is 50 times 4 minus 2 times 4, 200 minus 8, 192. So our answer for this problem, 192. So what are the key ideas in this problem? The key idea was 3D visualization and trying to visualize it 3D. That's probably the hardest part of the problem. And then from there, the thing to remember was when we folded, let's say AB down and it mapped BC, they have to be equal length for them to match up. So we use that to deduce a lot of information about length. And we also found this is 8, this is 8, this is 8, that's 8, because a bunch of stuff coincided on here. And then after that, we realized that we had the height, we had one of the legs of the right triangle base, we just needed to find the other one to find the volume. And to do that, we could also just find this leg, which corresponded to this value. And we now have to use this fact that this was 14. And using some backwards thinking, we went backwards and saw that, okay, we just need to find the value of HJ. The value of HJ is equal to AB, which is equal to BC. Oh, but that's equal to this length here, 8. So then this part is 8, and this part must be 6. And then we found this to be 6, this 8, this 8. So the volume is just 6 times 8 by 2 times 8, 192. Now let's talk about some pyramids. The volume of any pyramid is 1/3 times the base area times the height. And so it's very similar to prism, base area times height, except now there's a 1/3 factor. There's a formula you can memorize, it's not needed, but the volume of a regular square pyramid is √2/6s³, and a regular tetrahedron or triangular pyramid, √2/12s³. Now, these are good to know because they can save you some time, but you don't have to know them, as you can always just rederive it by using equilateral triangle area formula, or you can always rederive it by doing some Pythagorean theorem techniques. So, for example, and the reason we have to do it in terms of s is this time we're not actually given the height. And to derive this formula, if you're trying to derive it, what you would have to do is drop the altitude to the center, and then see that this height, we form a right triangle. So from here, what we can do is draw the base separately. And the base is equilateral triangle because it's a tetrahedron. And then all the sides are SSS. We're essentially looking here in the center. We're trying to find what is this length of one of these red segments I drew. And the trick to doing this is realize that there's 3 parts of this angle that make 360. Each of them must be 120. So then if we know this whole thing is 120 over here, we can drop the altitude to the base, and then two parts that are 60 here, a 30 part here, and 30 here, because this is a 90-degree angle since we dropped the altitude. And these are 30, 60, 90 triangles. This whole thing is S, so this part over here will be S over 2, and S over 2 is the side opposite 60 degrees, which means this side over here must be S over 2 root 3 because the side opposite 60 degree is root 3 times bigger than the side opposite 30 degrees. And then this side, hypotenuse, is just double of the short leg. So double of S over 2 root 3 is just S over root 3, which is the length of the hypotenuse. And that's just what's over here, S over root 3. And now what we do is we notice that the height, this, and S form a right triangle. So we get that h squared plus, or it should be S over root 3 here, right? S over root 3 as we discovered. H squared plus S squared over 3 equals S squared. So h squared is 2S squared over 3. And then from here we can get that taking square root, h equals root 2 over root 3 times S. And from here, I'm not going to do the rest, but from here, now that you solve for the height, you can easily find the base area using the root 3 by 4 side squared formula, and then you just plug it in here. 1/3 times the base area, root 3 over 4 side squared, times the height, which is this, root 2 over root 3, S. And then from there, you can just plug it in here, simplify, and you'll get this nice looking formula for the volume of a tetrahedron. And there's something similar for pyramid, but I won't show that for the sake of time. But the idea is you look at this diagonal here, H 90-degree angle, Pythag theorem. These are only for regular, so all sides equal and everything symmetric. Okay, now let's solve a problem that uses this. Triangle ABC with sides 5, 6, and 7 has one vertex on the positive x-axis. Let's say that's A. One vertex on the positive y-axis, B, and one vertex on the positive z-axis, C. So A, B, C. Let O be the origin. What is the volume of tetrahedron OABC? So this is like a corner, you can imagine. We're given, as you can see in the diagram, sides 5, 6, and 7. I've already marked them for you. 5, 6, and 7. But we're trying to find the volume of the tetrahedron. This is not a regular tetrahedron. These formulas won't work. And just like any other problem, to do this, we need to find base area, which is that, and the height. And if we can find the base area and the height, we can find the volume. And to find the base area, we just need to find A and C. And to find the height, it's just B. So essentially, we need to solve for these three variables, A, B, and C, to find the volume. How can we do that? Well, we're given these conditions, 5, 6, and 7. So we have to somehow use those conditions, that AB is 5, BC is 6, and AC is 7. Okay, so first things first, BC equals 6, this one. Focus in on this one. Way too thick. Okay, that's better. So how do we use a condition that BC is 6? Well, notice here that it has one, this is the origin, right? And then this is x-axis, y-axis, and z-axis. So what that means is that this is going to be a 90-degree angle right here. Why is that the case? Well, because one of these points is literally on the y-axis. One of them is on the y-axis, and one is on the x-axis somewhere. So they will form a right angle because the axes are perpendicular. And the same thing is true with the y, x, and z, and y and z axis. It's very similar logic. axes are always perpendicular, so that's 90, and these two are also perpendicular. So we can draw a bunch of 90-degree symbols, but I'm not going to draw the rest of them because it should be clear by now, right? Or maybe I'll just draw them just to make sure. And even though they don't look right at all, do they? Like, this is not right angle, is it? But the key thing to remember here is this is a 3D diagram. So it's not going to look right because we're just seeing a 2D version of it. Okay, so now how do we use these right angles? If you remember from the previous few videos, right angles are a good sign to use the Pythagorean theorem. So let's see how we can use Pythagorean theorem for this over here. BC equals 6. And it forms a right, let's just draw this triangle separately. B, C, and 6, just like that. That's a right triangle, right? I just drew this side over here. And that means by Pythagorean theorem, b squared plus c squared is 36. Okay, and now similarly over here, that's 5. So we have a squared plus b squared equals 5 squared, which is 25, right? By this triangle, this right triangle. And now we have this one at the bottom, which I'm going to redraw just so you can see that it's really right. There's a right angle there, so hopefully help with the visualization process. A squared plus c squared equals 7 squared, which is 49. So now we've got 3 equations and 3 variables. We can know how to solve 3 variable equations. A squared plus b squared equals 25. B squared plus c squared equals 36. And a squared plus c squared is 49. Now, if you remember from the algebraic manipulation video, which is part of the same playlist, Mastering AMCA, we realized that when an equation is symmetric, we want to take advantage of the symmetry. And it's symmetric here. AB, BC, AC. This is a symmetric equation. So what we can try and do is find a squared plus b squared plus c squared, because that will help us use the symmetry. And because these 3 equations are symmetric, we can add them up together to form a squared, 2a squared, b squared, 2b squared, c squared, 2c squared equals 25 plus 36 plus 49. That is 110, because 25 plus 36 is going to just be equal to 61. 61 plus 49, 60 plus 50, 110. And now we divide by 2 from the whole equation to get a squared plus b squared plus c squared is 55. Okay, so now we have this quantity, but we're trying to solve for a, b, and c. How should we do that from here? Well, the key idea is now we know their total sum, and we know all of these sums: a squared plus b squared plus c squared, a squared plus c squared. So what we can try and do, it's a very cool trick. Let's say we have this over here, this equation. Sorry, I did not mean to erase that. So we can essentially subtract these 2 equations. To get c squared equals 30, or c equals root 30. And we can do something very similar for the rest of them, but we're running out of space here, so let's just make that tinier. Luckily, we're not doing this on paper, so there's no limits. And now let's also subtract the equation a squared plus b squared plus c squared equals 55 minus the equation b squared plus c squared is 36. That gives us a squared is 19, or that a is root 19 by just taking the square root of both sides. And finally, we have a squared plus b squared plus c squared minus a squared plus c squared equals 49, which gives b squared is 6, b is root 6. We've solved for A, B, and C. And let's just mark it on the diagram so we can see. A is root 19. A is root 19. B is root 6. C is root 30. Okay, so now what is the volume? And I'm just going to erase all of this so we can have some space to calculate the volume. Remember, like what I said earlier, volume is base area times height divided times 1/3. And there's actually multiple ways to calculate the volume here, depending on what you choose as your base. You can choose this as your base, you can choose this as your base, or you can choose this as your base. It doesn't matter, they'll all give the correct answer. For the sake of this, I'll just choose this bottom one as the base because it seems the most intuitively, it looks the most intuitively like the base, right? After all, it's the bottom one. So the volume of that orange base is half BH, which is half times root 30 times root 19. The volume is 1/3 base area times height. The base area we found to be this, half root 30 root 19. The height was just root 6. So we can simplify this to get that 1/6 times root 30 times root 19 times root 6. Now, this is not simplified fully. Notice that we can simplify the square root expression. Root 30 has a factor of root 6. Root 6 has a factor of root 6. So we can rewrite this as 1/6 times root 6 times root 5 times root 19, and then times root 6. But then these root 6 times root 6 is just 6, so this becomes 6 over here. 6 cancels. We're left with root 5 times root 19, which is root 95. And that's our final answer, root 95, the volume of this tetrahedron. So this was a problem that just came down to using these three informations, writing three equations, Pythagorean theorem, and then solving for each of the variables, plugging into 1/3 base area height. And the key idea was noticing these right angles here that must be true because they're on the axis, and then we just use Pythag theorem, and how we cleverly added the equations up to take advantage of the symmetry. And then subtracted all the equations one by one to get the values of a squared, b squared, and c squared. Okay, now we're going to talk about cylinders. But we're going to do that all in the next video. You can click on the next video. We're talking about curved 3D shapes over here.